Hello, welcome to Math 104. We are going to continue with our notes for Unit 3. We left off on page 3. We just finished talking about exponent rules and how we actually apply them. We really want to get a solid understanding of these rules prior to moving into understanding radicals. So we actually had one more at the very bottom of page 3. So let's take a look at that and then we'll dive right into radicals. Okay, so we want to begin by noticing our coefficients here. So we have a 12 divided by a negative 18. If I focus my attention to just the coefficients, I can say to myself that I definitely have the option here to reduce by dividing out a common factor. What I want you to notice is we can definitely divide out a 2 from each. First off, I notice that I have a 12 over a negative 18. So when I go ahead and rewrite my answer, my simplified form, I actually want to bring the negative out in front. So I'm going to write the negative in front of the fraction. I could bring that to the numerator, but it is preferred to bring that negative either in front or up top. So then I'm going to reduce my 12 and my 18 by dividing out a 2. If I divide both by 2, I get 6, and then we divide here, and we also get a 9. Notice that that implies that I can reduce even further, which I will do in just a second. I want to show you that it's okay to do this in steps. Next, I'm going to focus on my bases that have negative powers, and it just so happens that each of my bases, x and y, in the numerator and in the denominator, all have negative exponents. What we learned is that if you have a base with a negative power in the numerator, it's going to move to the denominator. And if you have a base with a negative power in the denominator, it's going to shift to the numerator. When we shift the base with that power, the power then becomes positive. So rewriting, I notice that I now have in my numerator an x to the positive 3 and a y to the positive 1. In my denominator, I have an x to the positive 2 and a y to the positive 5. So far, so good, but I definitely need to reduce further. Next, notice that I can absolutely divide out a 3 from each of my coefficients. So I've got negative, and then 3 can go into 6 twice and 3 into 9 3 times. Next, I'm going to focus on my base x. So I have 3 factors of x in my numerator, but only 2 factors of x in my denominator. According to the quotient rule, we're going to subtract the powers. So notice we're left with a single x, and it's going to be left in the numerator because it's heavier in the numerator. Similarly speaking, we have a y to the first divided by y to the fifth. Use the quotient rule again. We're going to keep the base, subtract the powers, leave it where it's heaviest. So I'm going to leave a y to the fourth in my denominator. 1 factor of y over 5 factors of y. Divide out 1 factor and you're left with 4 of them. And that is your final solution. So I wanted to show you how we can do this step by step in proceeding through the problem and focusing on simplifying. Okay? Beautiful. Let's go ahead and turn the page and get into 2 more final examples before we look at radicals. So let me go ahead and move the camera just a touch. We have 3 to the first, x to the first, y to the negative second power. All of this is being raised to the third. We are going to distribute, right, because we are applying the power rule. So essentially we are recognizing this is power times power. So we get 3 to the third, x to the third, and y to the negative 6. Next, we're going to look at each base and simplify wherever possible. So 3 to the third we know becomes 3 times 3 times 3, which is 27. X to the third, we're not going to touch that. We're going to leave it in the numerator. And then I see that I have a base with a negative power, so I'm going to move that to the denominator and then change the exponent from negative to positive. I can't simplify anything else, so we're done. No big deal. Last example on exponent rules, same idea. We're going to go ahead and distribute power times power. The one thing I want you to know and to get comfortable with is that the negative is inside the parentheses, which is being raised to the third power. When we have a negative times a negative times a negative, we recognize that our solution is still going to be a negative. Think about the fact that when you square a negative number, it becomes positive. When you actually raise a negative quantity, in parentheses, to an even power, it becomes positive. And just consider that every time you have two negative numbers, when you multiply them, you get positive. So just kind of keep that in mind as you progress through these problems. Don't let the sign kind of escape you. So we're going to now distribute power times power. We get 2 to the third. We have x to the 12th, z to the negative 6th power. Now, I'm multiplying this entire set of parentheses by the 4x squared z to the 8th. So it's still all just a product. So 4 to the first, x to the second, z to the 8th. The next thing I'm actually going to do is I'm going to evaluate this 2 to the third. So this leaves me with a negative, and then 2 times 2 times 2 is 8. So I'm just going to rewrite it for a moment. And actually, I'm going to keep the z to the negative 6 the same way as well. I want to show you something that you are allowed to do. At this point, we are using the product rule, right? So first off, negative 8 times 4, here are my coefficients. I can definitely multiply these two. If I did not evaluate the 2 to the third, I cannot say 2 times 4 is 8 and then 3 plus 1 is 4. That's like absolute insanity. That makes absolutely no sense. So we're going to evaluate first, apply the exponents before we multiply, right? Think PEMDAS, order of operations. Apply the exponent before we multiply. So negative 8 times 4 is negative 32. And then we move to, okay, let's apply the product rule. You keep the base, add the powers. X to the 12th times x to the second, keep the base, add the powers. 12 plus 2, 14. Then we move to the z's. We are going to use the product rule again, even though we have a negative exponent. I'll show you why. You're going to keep the base, add the powers. Well, if you keep the base and you take negative 6 plus 8, you get a positive 2. And just like that, we're done. So something to think about in terms of applying the product rule versus using the negative exponent rule first. We totally can. If you wanted to write this as negative 8x to the 12th over z to the 6th and then cancel with the z to the 8th, that's fine. That's not a big deal. I just wanted to show you an alternative because essentially here we're simply applying the product rule. Keep the base, add the powers. All right? As a little side note, take a look at the box up top. X plus y to the third, is that the same as cubing each term? No, absolutely not. That is not correct. We learned that x plus y to the third power would actually have to be rewritten. We would have to write it as x plus y times x plus y times x plus y. We are literally multiplying x plus y by itself 3 times. So it's really important to keep that in mind. With our second example, we have x times y all raised to the third. So this is a great place which allows us to apply the power rule. So yes, this does work where you distribute power times power. Lastly, notice we have two bases in the set of parentheses and they're both being raised to the third power. So by saying this becomes 2x to the third, that means you're totally neglecting the 2. So in this case, this is completely incorrect. We would actually have to write the answer as 2 to the third, x to the third. You don't ever want to leave a base out. It's almost like saying, I know I'm cubing this too, but I don't want to write it that way, right? You can't do that. We want to make sure that we're consistent by applying that rule to all bases. Good. At that point, we're ready to move into radicals, okay? Roots and radicals. So first off, I want you all to be familiar with the notation, right? So this is essentially the nth root of a, where we have our radical symbol, we have our index. I like to call the index a root, right? So it's the nth root, and we'll talk more about that in a second. And then anything that's underneath the radical is called the radicand, okay? Here we have the radicand. When we are evaluating square roots, we're very familiar with this. This is something we've seen 1,000,001 times. So when we evaluate a square root, we understand perfect squares. We understand properties of perfect squares. So first off, we know that square root of 25 is 5. And the reason for this is because 5 times 5, which is 5 squared, is 25. So 25 is a perfect square, right? So I want you to kind of keep that in mind. I've provided a table here just to give you some quick radicals, some quick square roots. Square root of 4 is 2, square root of 9 is 3, etc., etc. So if you just want to fill this in so that you have your little cheat sheet, that's totally fine. You should be familiar with perfect squares higher than 100, of course. So 4, 9, 16, 25, all the way, etc. Those are all perfect squares. The very first one is obviously square root of 1. That's not included in the chart, but we know that square root of 1 is simply 1. Okay, so we have something called a principal square root and a negative square root. I want you to notice where the negative is located. The negative is located in this example in front of the radical, which is actually really important. So for instance, if I had the square root of 16, I would say, well, the square root of 16 is simply 4. Looking at my second example, I have negative square root of 16. Well, let's apply the square root to the 16. So if we apply the square root to the 16, that gives us 4. And then, of course, we don't want to neglect the fact that it's a negative quantity. So we bring the negative in front, and there we have a negative 4. Now, we have a couple follow-up questions, and those are, can the radicand be 0? Can I have the square root of 0? Yes, absolutely. The square root of 0 is simply 0, right? Because 0 times 0 is 0. So that's totally, totally fine. But can the radicand, and remember we're talking about square roots, can the radicand be negative? Is it possible, for instance, to take a square root of negative 36 and say that, okay, it's just negative 6? Well, let's test that theory. Because my root is 2, I should be able to take my solution here, and I should be able to square it so that I can get the original radicand. But here's the issue. Negative 6 times negative 6 is actually a positive 36. So this is actually not valid at all. What we've seen in the past time and time again is that the square root of a negative is actually not a real number. It's something called an imaginary number, which we will see later on in this unit. So we are not dealing with real numbers when we try to take the square root of a negative 36. And we know this because a negative 6 times a negative 6 is actually positive, but not negative. So in order for a square root to be a real number, the radicand must be positive. That's something I want you to keep in mind. Okay, essentially that radicand, that a, must be greater than 0. Beautiful. And this is only dealing with square roots, or even roots to be exact. Okay, let's turn the page and continue with this idea. I wanted to provide you with an opportunity to see what a square root function looks like. So we have our table here, and we can actually input values and kind of talk about what's happening. So for instance, at the point when x is equal to negative 4, and we plug that in, y is equal to the square root of negative 4, we're going to say not real, right? So we actually don't have a point on the graph to plot. It's not a real number. Same thing with y is equal to the square root of negative 1. This again is not real. But when we start to plug in values that are greater than or equal to 0, and by the way, I want to make a quick correction. I want to note here that your radicand must be greater than or equal to 0. As we saw before, it can be 0. So we have y is equal to the square root of 0, which is 0. So my first ordered pair is the point 0, 0, which I have plotted here. Next, I'm going to evaluate the function when x is 1. Y is equal to the square root of 1, which is just 1. There's my next point on the function, 1, comma 1. Let's plug in 4. That's my next perfect square. So the square root of 4 is 2, so my next ordered pair is 4, comma 2, x then y. Notice I've plotted that point for you, 4, 2. Lastly, The square root of 9 results in 3. So my next point on the function is 9 comma 3. And then, of course, so on and so forth. So I want you to be familiar with the square root function and the shape that it takes on. Okay? So we're noticing that our function is essentially continues in the positive direction. So essentially we're moving in quadrant 1. Okay? We do not have any negative values here when we're looking at our inputs versus outputs. So we're going to evaluate the following using a calculator. We're essentially just going to plug this in, and we're going to determine if we have a rational number, an irrational number, or an undefined number. Okay, so we have the square root of 64. If we plug this in using our calculators, we know the square root of 64 is 8. This is definitely rational. Recall that rational numbers involve integers, whole numbers, natural numbers. It also includes terminating decimals and repeating decimals. So like 0.125, terminating decimal. 0.333333333 repeating, rational, terminating decimal. Or excuse me, repeating decimal. Duh. Okay, so if it repeats, that's fine, it's rational. If it terminates, it's also rational. Okay, and again, that includes integers, whole numbers, natural counting numbers. Let's take a look at the next example, square root of 3. So let's punch in square root of 3, press enter, and notice what we have here. 1.732050808. Okay, it looks like it is not a repeating decimal. It also looks like it's not terminating. So this is actually, and I'm going to write 1.732 ... and we're going to note that this is irrational. Doesn't terminate. And doesn't repeat. We can use different technology to verify that that is in fact the case. And then lastly, we have the square root of negative 25. Again, I want to show you. Let's punch in the square root of negative 25. Notice we get an error. So this is just a way to really hone in on the fact that we cannot take the square root of a negative number. So this is going to be not real, or in other words, undefined. Okay? Perfect. Now let's talk about cube roots. When we think of cube roots, I want you to think of perfect cubes, right? Let's look at the table here on this side. First off, we know the cube root of 1 is 1, right? Because 1 times 1 times 1 is 1. The cube root of 8 is 2, and that's because 2 times 2 times 2 is 8. Similarly, cube root of 27 is 3. 3 to the third is 27. Cube root of 64 is 4. Cube root of 125 is 5. Cube root of 216 is 6. Cube root of 343 is 7. And then etc., etc., etc. I will tell you in this class, typically we won't be looking at cube roots higher than 343. But really, it's not tough to verify whether or not you have a cube root. Let me demonstrate to you how we would punch this in. For this particular calculator, the one we are using for our class, we could do this in one of two ways. I'm going to show you the way you should be familiar with, at least at first, until we talk about fractional exponents. So right now, we want to type in the cube root of 8. So I want you to notice here above the caret key, we have the x root symbol, but it's in yellow. So that x has to be defined. That root has to be defined. So we want the cube root. So notice that I type in 3 before I type in the x root. So I'm essentially saying I want this to be a cube root of 8, and it gives us 2. Let's do it again. 3, use the function right above the caret. So second caret gives you the x, the root, where we're saying the root is 3. And let's type in 27. So the cube root of 27 is 3, etc., etc. This is really nice because it'll allow you to essentially use higher order roots as well. Okay? Perfect. Going back, notice that we have, therefore, cube root of 27 is 3 because 3 to the third is 27. Now, interestingly enough, we have the cube root of negative 8. We actually can take the cube root of a negative number. Remember, negative times a negative times a negative remains a negative. So cube root of negative 8 is in fact negative 2. It is a real number. So let's write out that we know this because when we cube negative 2, we get negative 8. So that works. In order for a cube root to be a real number, the radicand can be any real number, which is super cool. Positive or negative, it can be any real number. I want to show you what this function looks like. So we have our graph here, which is already drawn, but I do want to punch in my ordered pairs to show you where everything is coming from. So we have y is equal to the cube root of negative 8, which is negative 2. So our first point here, we have negative 8 comma negative 2. Let's continue. We have y is equal to the cube root of negative 1, which is a negative 1. So we have the ordered pair, negative 1, negative 1. Here's my point. Y is equal to the cube root of 0, which is simply 0. So the origin is also a point on my function. Y is equal to the cube root of 1, which is a positive 1. So there's my next point, my next ordered pair on the function. And then lastly, y is equal to the cube root of 8, which is 2, a positive 2. So 8 comma 2 is yet another point on my function. So I want you to notice in this case that if I covered up this lower half of the function, it should remind you of the square root function from before. But with the cube root function, notice that we also can evaluate our inputs in the negative direction as well, because that will result in real numbers. So we can definitely graph that. Excellent. Let's go ahead and turn the page. Let's practice evaluating using a calculator. So we're going to start with the cube root of 64. Just punching this in, we notice that we get 4. Let's evaluate the cube root, and I'm just going to change the values here, of negative 125. That gives me negative 5. Perfect. Notice we have the cube root of 27 over 8. What I want to show you is, let me do this a couple ways. So I want to type in the cube root. Let's fix that. I want to type in the cube root of a fraction. So what I'm going to do here is input parentheses, and I'm going to try typing 28 ABC 8, just so that my calculator understands it's taking the cube root of both the numerator and denominator. Luckily, that worked out, so I get 1 1/2 as an answer, but I actually want an improper fraction. So I'm going to press second ABC to change to improper fraction form, and we get 3 over 2 as my result. What I want you to consider is what that means. What this is implying is that you want to take the cube root of 27, and you also want to take the cube root of 8. So the cube root of a fraction is the same as a fraction of cube roots. That's something we will definitely see time and time again in the future. Let's go ahead and take the cube root of 9 and see what happens. So we want to type in 3, the xth root of 9, and then notice we get a decimal, and that's okay. This is still a real number. It just happens to be irrational. So 2.0800838 ... So it's still a real number, but what I wanted to kind of point out is that the cube root of 9 is not the same as 9 divided by 3. It's not the same, but we know that because essentially we're looking for a quantity times itself again to give us the radicand. Okay? Beautiful. Let's look at other radicals just to make sure that we're comfortable with this idea. So for instance, notice we have the 4th root of 16. When you think of the fourth root of 16, I want you to envision to yourself what number times itself 4 times gives you the radicand, which is 16, right? When you think about it, we're going to have to be pretty small. If you had guessed 4 times 4 is already 16, so that's not going to work. Imagine 4 times 4 times 4 times 4, that's going to be much, much bigger. So if we go even smaller than that, we have 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. We see that the fourth root of 16 is 2. And again, let me write down why. So we see the fourth root of 16 is 2, and that's because 2 to the fourth is 16. Let's move to the sixth root of 64. So again, same idea. Let's think about what we would be multiplying by itself 6 times to get 64. I'm pretty sure you're automatically jumping to, well, it's got to be 2 because 2 to the 6th is 64. Just to show you how you would punch this into the calculator, you're going to type in 6 x root 64 because it's the sixth root of 64, and it gives you the value 2. And that's because 2 to the 6th power is 64. Okay, let's take a look at the negative fourth root of 81. So first off, the negative is going to stay since that's in front of the radical. The fourth root of 81, think of a number multiplied by itself 4 times. 3 times 3 is 9, times 3 is 27, times 3 is 81. So negative 3 is the correct solution here. And again, that's because, first off, we know that negative and then 3 to the 4th power is going to give us that negative 81. Now, I'm separating this because essentially that negative has to stay in front. So I want to bring the negative out front just so you can see what actually happens. You're applying the 4th power to that 3, that base 3. And that's what gives you the 81. But of course, we keep that negative. Now, I want to demonstrate to you in the calculator. So negative, let's see, actually, it's not going to keep the 4 in here. It's going to think something's totally different. Let's punch in the fourth root of negative 81. So you see here we have an even root. I don't need that parentheses. We have an even root. Let's check it out. Error, okay? So we can write does not exist. We can write not real. We can write undefined. And that's because essentially no number multiplied by itself 4 times will give you negative 81. Let's write down that because there does not exist a real number to satisfy this condition. There's no way to multiply a number by itself 4 times to give you a negative 81. It's just not going to happen. Let's take a look at the rest. Fifth root of 32. So same exact idea. We can use a calculator if we want, or we could think about what times itself 5 times. When you do this, you get 2, again, because 2 to the 5th is 32. I hope this isn't too monotonous. The fifth root of negative 32, now that's interesting. Let's type the fifth root of negative 32. I want you to keep in mind here that it's an odd root this time. So when we take the odd root of a negative 32, we actually do get a result. Negative times a negative times a negative times a negative times a negative, meaning 5 times, is still a negative. So this is definitely a real solution. So think about the fact that negative 2 to the 5th is negative 32. So that totally works. We want to take the fifth root of 243. When we punch that in, we see that we get 3. And that is because 3 to the 5th is 243. And then same idea here, because we're taking the fifth root of a negative number, we will get a negative result. And that is because negative 3 to the 5th is negative 243. So just some things to think about as you progress through these problems. Keep in mind, an odd root, you can have a negative radicand, but with an even root, you cannot have a negative radicand. Okay. We're ready to talk about changing expressions from radical to exponent and vice versa. When we have a base to a fractional power, that should indicate to you, if that fraction doesn't simplify and it remains a fraction, we actually have a radical on our hands. So we can actually rewrite this in radical form. Similarly, if we were to start with a radical, I want to show you the way in which you would write it as an exponent, as a base with a fractional power. So let me show you how I dissected this to essentially make the most sense to me when I was learning. So check this out. Notice here, I have the radical, the rth root, that's an r, the rth root of a to the p, right? The power p. The reason I chose these variables is because of the way we would rewrite it in exponential form. We keep the base, we keep our radicand, which is a, so we keep that base, and then the exponent becomes power over root. I like writing the exponent using p and r because first off, power over root. And then we could start to think, well, roots are in the ground, so roots should be in the denominator, right? So when we rewrite our expression in exponential form, remember that the root is in the denominator. Roots are in the ground. So a to the power over root, power over root, power over root, okay? Keep that in mind. If your base a is negative, your r, your root, must be odd, right, in order to be able to evaluate this. But let's take a look. So we want to write each radical expression in exponential form. We start with the square root of 6. Keep in mind this 6 is being raised to the first power. And when we say square root, we know that our index, our root, is 2. So to write this in exponential form, you keep the base and you write it as power over root. Power over root. Let's do it again. Here we have the fourth root of x. This is x to the first power, so you're going to keep the base. And your exponent is power over root. So the fourth root of x is the same as x to the 1/4. Let's take a look at the next example. We have 7 to the first power, x to the fourth power, y to the first power. So interestingly enough, we can write this in one of two ways. The first way is to say that my radicand, which is 7x to the fourth y, is going to be raised to the 1/3 power. Imagine here that if I place this radicand in parentheses, this is all being raised to the first power, power over root. But technically, if I wanted to write this completely in exponential form, where each base has that fractional power, then this becomes 7 to the power over root, x to the power over root, and then y to the power over root. Later on, we're going to figure out how to simplify something like this because you notice that my fraction here actually would result in a mixed number because my numerator is larger than my denominator. So we will learn later on how we would clean this up and simplify it. Okay, same thing here. We can look at this in one of two ways. We can say that so first off, we have 4 times the cube root of 3x to the second over 5y. We can rewrite this as 4 parentheses 3x squared over 5y, all of this raised to the 1/3 power. Think of this expression under the radical as a quantity being raised to the first power. and the root is 3, so power over root. This would actually be a great way of rewriting this in exponential form. If we wanted to open everything up, we can. It's just going to be incredibly messy. So I'm actually going to leave my answer just like that. Okay, because we're just practicing on how to rewrite this. Let's go ahead and turn the page. Okay. This time, we want to go backwards. So we want to write each exponential expression in radical form. And then we want to simplify if at all possible. Okay, for the first one, we have 4 to the power over root, 1 over 2. So my power is 1, my root is 2. Now that I have this written in radical form, the square root of 4 is simply 2, and I'm done. My second example is negative 8 to the power over root. So I have negative 8 to the power of 1, and my root is 2. But can I take the square root of a negative 8? No. So my answer here would be undefined or not real. Next, I have 6x to the second y, all raised to the 1/3 power, power over root. So think of this as 6x squared y to the first power, but your root is 3. So it's the cube root of 6x squared y. So we really could write it without parentheses in this case. We can write it as the cube roots of 6x squared y. And keep in mind, you cannot evaluate the cube root of 6. There's nothing, there are no whole numbers multiplied by itself 3 times that give you a 6, right? 2 times 2 times 2 is 8, not 6. Lastly, I was hoping that this would be a little bit of a trickier scenario because we have to be careful with what's actually being raised to a power. Notice we have 5xy to the 1/2. This actually implies here that this y alone is being raised to the 1/2 power. The 5x is not. If we wanted to raise all of this to the 1/2 power, we would need parentheses, just like we saw in our previous example. So we're going to bring the 5x down, and then we have y to the 1/2. So y to the first power to the root of 2. So the second root, or essentially square root of y. Here is my final result. This is how I would rewrite my radical form in exponential form. Keep in mind, only the y is being raised to that 1/2. So just as a summary, if you see a base to the 1/2 power, you're taking the square root. If you see the base to a 1/3 power, you're taking the cube root. Anytime you have a different number greater than 1 in the numerator, that's going to be your power, where the denominator is always your root. Roots are in the ground, roots, denominator, hopefully that makes sense. Power over root, power over root. Hear that in your minds as you do this again and again and again. We're going to simplify the expressions containing rational exponents. Let's take a look. 25 raised to the 1/2 power, that's the same as taking the square root of 25. The square root of 25 is 5. 8 to the 1/3, that's the same as the cube root of 8. The cube root of 8 is simply 2. Notice here we're taking the we're raising the 81 to the power of 1/2, not that negative. We would need parentheses around the negative 81 in order to raise the entire thing, the entire quantity to the 1/2 power. That's not what's happening. So I'm going to circle the 81 raised to the 1/2 power. So it becomes a negative square root of 81. The square root of 81 is 9, because 9 times 9 is 81, and then you bring that negative sign down. Negative 8 to the 1/3 power, that's the same as taking a negative 8 and cube rooting it. So we have the cube root of negative 8, which gives us negative 2. Lastly, we have something very interesting here. We have 27 to the negative 1/3 power. What we learned when we had negative exponents was that we always wanted to circle the base with the negative power. And if it's in the numerator, we want to move it to a denominator. So then that means this becomes 1 over 27 to the positive 1/3 power. Well, we know how to write 27 to the 1/3 power. That becomes 1 over cube root of 27. And 1 over cube root of 27 becomes 1 over 3. So that's definitely one of the things I want you to be very careful of, is if you have negative exponents, you should really move the base with the negative power first, just to simplify this, so that you have positive exponents and then apply that exponent, okay? So move the base with the negative exponent to either the numerator or denominator, whichever one it's got to shift to. Make that power positive, and then of course, notice I can rewrite and evaluate. Perfect. Take a look at the next section. Write each radical expression in exponential form. Okay. Then reduce the fraction in the exponent to lowest terms if possible. Remember that your exponential form is base raised to the power over root. That's going to be really helpful to keep in mind. So my base in this case is 2. I have the 5th root of 2 to the 8th. My base is 2. My power is 8. And my root is 5. So 2 raised to the 8/5. We're not going to reduce that. There are no common factors, so we're going to leave it as is. Next, we have the 6th root of z to the 2nd power. Keep the base. Then we have power over root. But we recognize here that 2 over 6 does reduce. So this becomes z to the 1/3 power. So interestingly enough, the 6th root of z to the 2nd power is the same as the cube root of z. That's kind of interesting to note. And I'm just going to rewrite it here so that you can see it. According to what we found here, these two expressions are exactly identical. Something very interesting is happening here. So we're just going to think about this for a moment. Next, we have 3 times the square root of xy quantity to the 4th. So we have 3 times, we have xy to the power over root. When we simplify that power over root, we get 3 times the quantity xy to the 2nd power. And then, of course, we know how to apply the power rule. So this becomes 3 times x squared y squared, right? We are going to distribute that power. So interestingly enough, this became 3 times x squared y squared. That's a very interesting property. That's a very interesting fact that just occurred. I could have rewritten this to show you that 3 times the square root of xy to the 4th is the same as 3 times xy to the 2nd power. That's pretty interesting. I want you to notice what happened with that power. When we took the square root of xy to the 4th, notice what happened to that power. Lastly, we have the 4th root of ab all raised to the 3rd power. Believe it or not, we can actually rewrite this in a couple ways. So first off, I want to begin by rewriting what's in parentheses. So the 4th root of ab is the same as taking ab and raising it to the 1/4 power. But keep in mind that we are raising this quantity to the 3rd, which is in essence the same as ab to the 3/4 power. Remember, you're going to multiply power times power. 1/4 times 3/1 is the same as 3/4. Okay? So I want you to consider the similarities here. The 4th root of ab to the 3rd power is the same as ab to the power over root, even though that power happened to be on the outside. I do want to point out that we could have had that 3, that power of 3, inside the set of parentheses. So for example, if instead we had the 4th root of ab to the 3rd, we actually have the exact same expression, ab to the power over root. It's actually going to be identical. So something to think about in terms of where that power is located. Good. Let's go ahead and turn the page. At this point, we should, like if you're watching at a later date, go ahead and pause the video and try examples 19 and 20. I want you to really make sure that these ideas are completely making sense to you. So you try these and then you'll compare your work with mine. And like I said, especially if you're watching this at a later date. But for now, I will breeze through these. I kind of feel like there's an excess number of examples. And I'm kind of tempted to let you just have these and then, you know, check back in later when I actually scan the notes. But I'll complete these rather quickly. So if you're watching concurrently right now, so, you know, hopefully this was a head start for you to go through the problems and try it out on your own and then compare your work with mine, okay? But yes, if you're watching from home, go ahead and pause, try these 2 examples, example 19 and 20, prior to playing the video again, okay? Let's take a look. 8 to the 2/3, so we're gonna write in radical form. We have the cube root of 8 squared. So we're writing each exponential expression in radical form. I want you to notice here that I can evaluate this. I also want you to notice that I placed the 2 on the outside. So the reason I did that is because I know the cube root of 8 is simply 2. And that 2 squared is 4. So I was able to actually evaluate this expression. I find sometimes it can be very helpful to look at this in a couple different ways. Let's bring the 2 on the outside so that we can evaluate the cube root. X to the 2/3, power over root. We can write it in 2 ways. We can write it as the cube root of x squared, or we can write it as the cube root of x squared. It means the same thing. 6 ab to the 3rd raised to the 2/7, so we have 6. Notice it's power over root, so my 7th root of ab to the 3rd raised to the 2nd power. Or we can write 6 times the 7th root of ab to the 3rd, all raised to the 2nd power. That's another way of rewriting this in exponential form. Lastly, x to the 9/5, we have the 5th root of x to the 9th, or the 5th root of x raised to the 9th. Okay, a couple different ways of looking at it. Good. For example 20, we want to simplify expressions containing rational exponents. We essentially want to write in radical form. So 27 to the 4/3 power means power over root, the cube root of 27, which we know we can take. 3 times 3 times 3 is 27. So the cube root of 27 is 3, but we still have the 4th power. So I think about 3 to the 4th as 3 times 3 is 9, 3 times 3 is another 9, 9 times 9 is 81. So we evaluate and we get an 81 as our final answer. Next, we have 4 to the 3/2 power. So we have the square root of 4 raised to the 3rd power times the cube root of 8. The square root of 4 is 2. The cube root of 8 is 2. And then 2 to the 3rd times 2, well, this becomes 2 times 2 times 2, which is 8, times 2, which is 16. And there's our final answer. Lastly, we have 32 to the negative 2/5 power. Well, I have a negative power, so I'm going to move this down. This becomes 1 over 32 to the positive 2/5 power. This becomes 1 over the 5th root of 32 raised to the 2nd power. Well, the 5th root of 32 is going to give us 2, because we know 2 times 2 times 2 times 2 times 2 is 32. So this gives us 1 over 2 squared, which means my final result is 1 over 4. All right. If you wanted to use your calculator to evaluate rational exponents, like the fractional exponents, that's actually really, really simple. Let me show you. So for instance, if I wanted to take the 196 and raise it to the 1/2 power, which by the way is the same as taking the square root of 196, I can simply say, let's take the 196 and raise it to, now use parentheses here. You want your calculator to understand that you want to raise your base 196 to the 1/2 power. And it interprets it as, okay, I get what that means. That means the square root of 196. Okay? Notice here we have 343 to the negative 1/3. And actually, I'm going to show you the one above it. I'm going to show you the one above it first because we went through each of the individual steps and proved that 32 to the negative 2/5 is 1/4. Let's check this out. 32 raised to the, use parentheses, negative 2/5. Now notice it gives you a decimal, 0.25. But if you want a fraction, we want to convert from fraction to decimal. First off, a quarter, you know a quarter is 1/4, right? But if we wanted to prove it, you want to press second, and then notice this key PRB above it says F to D. That means fraction to decimal or decimal to fraction. So we press that button and we get 1 over 4. Okay? If we went through the same process, the 343 to the negative 1/3 power is the same as 1 over 343 to the 1/3 power, which is the same as the cube root of 343 in the denominator. So when we take, for instance, 343 and we raise it to the 1/3 power, we see that we get 7. Now we're just going to do this using our calculator. Let's take 343, raise it to the negative 1/3 power. We get this crazy decimal, but let's change it into a fraction and see what we get. And we also get 1 over 7. All right. Using the calculator is a great way to check your work. Make sure you're not relying on that for all of your answers. You should still have an understanding of how to move through fractional exponents, like what it means and how to actually apply this. Okay. Simplify radical expressions. So we're going to write each radical expression in exponential form and then reduce the fractional exponent to lowest terms. We're then going to rewrite the answer as a radical expression if necessary. Okay? This one's going to be really interesting. Same idea. We have our base. We want power over root. Your power is 4, your root is 8. Power over root. 4 over 8 reduces to 1 over 2. So this becomes y to the 1/2, right? Because we simply divided each by 4. Well, y to the 1/2 can be rewritten in radical form to become the square root of y. Power is 1, root is 2. Okay, let's rewrite this second example. My radicand is a squared b to the 3rd c to the 1st. And my power is 12, where my root is 4. So 12 over 4, power over root. This becomes a to the 2nd, b to the 3rd, c to the 1st, raised to the 3rd power, because 12 divided by 4 is 3. Well, now I can finish this. I can distribute that power of 3 throughout applying the power rule. And that leaves me with a to the 6th, b to the 9th, c to the 3rd power, and we're done. There's no need to write anything in radical form because it was a whole number exponent. Our exponent was 3, so we just applied the power rule. Okay. Next, let's look at the craziness that's going on. First off, we have the square root of the cube root of x. Okay, first things first, we could do this a couple different ways. We can work from the inside out or the outside in. It really doesn't matter in this case. So we're taking the square root of this quantity. So let's start there. Here's the cube root of x, and we're taking the square root of the cube root of x. That's the same as raising that quantity to the 1/2 power, right? Because this pertains to the square root. Now I'm going to rewrite what's in here. The 3rd root, or the cube root of x, can be rewritten in exponential form as x to the 1/3 power. But keep in mind, I still have that 1/2 on the outside. Power rule says power times power. Remember, when you multiply, you go numerator times numerator over denominator times denominator. So this becomes x to the 1/6 power. Now that we have x to the 1/6 power, we can rewrite it in radical form. Power over root. My root is 6, and my power is 1. And there is your final result. Power over root. I'm going to keep saying it because I really want that to sink in, and I want you to even say this out loud when you're at home trying this on your own. Okay, so applying the rules to exponents to rational and negative exponents, for this page, you're essentially going to want to remove all negative exponents, and then you want to rewrite it as a radical and further simplify as possible. I actually want to leave you with this page to try on your own. So try this page on your own. Using everything that we've learned, I would like you to go ahead and kind of sit with these different problems and make sure that you're being careful about how you apply the exponent rules to each of these problems. The one piece that I would like to show you first is, and the only one I want to show you really quickly, is this second one. If I were you, I would apply the power rule. So this gives me 4 to the -2 over 3 to the -2. And then we could say every base with a negative power is going to move. So that 3 to the -2 moves up as 3 to the +2. 4 to the -2 moves down as 4 to the +2, and then of course that simplifies to 9 over 16. But I would like you to try the rest of these, just play around and see how this goes, okay? You'll definitely notice that you get creative at the very bottom, because remember, with the product rule, you keep the base, add the powers. With the quotient rule, you keep the base, subtract the powers. And then notice here, you're going to end up having to distribute. So because you're distributing to each term, you want to use the product rule, right? You're distributing, which means you're multiplying, so product rule. Keep that in mind, okay? Hopefully that goes really, really well for you. And it's okay to take your time and move through this slowly if you need to. All right? Perfect. Same exact idea with this page. It's just an extension of everything that we have learned so far. Because these are a little bit more complicated, I don't mind going through these with you. So for the first two examples here, it's just essentially recalling the same rule again, that power rule and how to apply this. Remember, we have power times power. So we have 5 to the 1st, a to the 3rd, b to the -4th. Let's take that 2 on the outside and distribute. So this becomes 5 to the 2nd, a to the 6th, b to the -8. Our b to the -8, this base moves to the denominator. So when it moves, it becomes a positive power. And then notice in my numerator, I still have 5 squared and a to the 6th. Well, 5 squared is 25, and we have a to the 6th. No big deal. Same exact idea here. I'll let you do this one on your own. Now, the more complicated problem is example 23. However, I don't want you to freak out. I don't want you to overthink this. I still want you to apply the power rule. So let's note here that this 9 is being raised to the first power. The first thing I would do personally is I would start by distributing the powers. Okay? So 1 times negative 1/2 is negative 1/2. Then we have x. Negative 2/3 times negative 1/2 is positive 2 over 6. Which, by the way, you're seeing what I'm seeing, right? You're seeing that this reduces, and I'll reduce it in a second. And then we have y to the 4th raised to the negative 1/2. So numerator times numerator, right? We get negative 4 over, and then 1 times 2 is 2. If it helps, put that whole number over a 1. 4 over 1 times 1 over 2 is 4 over 2. Let's clean these up. So we get 9 to the 1/2 power, x to the 1/3 power, if I can write. Ooh, that's a little sloppy. And then we have y to the negative 2. 4 divided by 2 is 2. Now, each base with a negative power is going to move. These are both in the numerator, so they're both going to shift to the denominator. So that means I'm left with x to the 1/3 all over 9 to the 1/2 power, y to the positive 2 power. Okay. Lastly, 9 raised to the 1/2 is the same as the square root of 9. So my final answer can be rewritten in 2 different ways. So it says simplify expressions with fractional exponents. We did, right? We simplified this. I could leave my answer as x to the 1/3 over 9 to the 1/2 is the same as square root of 9, like I said, so that's 3, y to the 2nd, and we can actually be done with this. If you wanted to write x to the 1/3 as a cube root of 3 instead, that's totally fine. But I believe for these examples, we're trying to go for fractional exponents and just simplifying those. So I would leave this as is. Okay? Good. For this second problem that definitely seems very complex, I don't want you to freak out. I don't want you to overthink this. If it helps, if it makes it easier on you, you can start by applying the product rule, or excuse me, the power rule. So we're going to go power times power everywhere we see. Let me try to squeeze this in here. So 1/3 here, and here, oh, and there. So we have w to the 5th raised to the 1/3 power. Remember, 5 times 1 over 3 is the same as 5 over 3, okay? You're going to write that 5 over 1 and then multiply straight across. So we get w to the 5/3 power. Next, 3 over 4 times 1 over 3. Notice the 3's divide out, so it leaves you with 1 over 4. So x to the 1/4 power. Then we have y to the 3 over 2 times 1 over 3 raised to the 1/3, which means you're going to multiply the powers. So those eliminate, those divide out. So you're left with y to the 1/2 power. That's in my numerator. 1 times 1/3 is 8 to the 1/3 power. X to the 1/2, so 1/2 times 1/3 is 1/6. And then we have negative 3 over 2 times 1 over 3, which is cool because the 3's cancel, and it leaves you with negative 1/2. So we have y to the negative 1/2. The next thing I'm going to consider is I have a single base of w, so that's not going to go anywhere. I have common bases here, so I'm going to apply the quotient rule. To apply the quotient rule, we need to keep the base, subtract the powers, and leave where it's heaviest. So I'm going to start by noting here, first off, that I have w to the 5/3, that's not going to change. 8 to the 1/3, that's the same as cube root of 8. Cube root of 8 is 2, so I'm just going to evaluate that. Quotient rule, keep the base, subtract the powers. So let's go ahead and do 1/4 minus 1/6. When we subtract fractions, we need an LCD. So I'm going to multiply the first fraction by 3 and the second fraction by 2 so that I have common denominators. So I have 3/12 minus 2/12. That means my numerator was larger than my denominator. 3/12 minus 2/12 is 1/12, and that's going to stay in the numerator with x. Next, I have y to the 1/2 over y to the negative 1/2. Keep the base, subtract the powers. This means I have 1/2 minus a negative 1/2. Or, check this out. Take the base with a negative power, bring it up top. This leaves me with y to the 1/2 and another y to the 1/2. Well, according to the product rule, you're going to keep the base and add the powers. So we have w to the 5/3, x to the 1/12. When we add a half and a half, we get a whole. So it's y to the 1st all over 2. That is definitely an involved problem, but it is not impossible. And it is not something outside of the realm of skills and abilities that you have. You just want to be very deliberate and careful as you move through this kind of a problem, step by step. So as a recap, I applied the power rule by multiplying power times power. Then I moved my base with a negative exponent up top just to clear that out. And then I applied my quotient rule. Because I had a base x in the numerator and denominator, I needed to keep the base and subtract the powers. Once I had my y's on the same level, they were both in the numerators, I can then combine these using the product rule. Keep the base, add the powers. 1/2 plus a half is a whole. And we're done. Okay? Piece by piece, yes, it's complicated, but it's not outside of your skills, so please don't fear problems like this. I want you to embrace them. It just gives you an opportunity to tie in all of the skills that you've learned together. We have another page of examples of the same stuff. I swear, I feel like I way overdid this, so I apologize. I feel like it's, beating a dead horse at this point. I do want you to give these a shot, just applying all of the rules. I apologize that there are so many examples of the same thing again and again and again. I think really the motivation behind this was it can be a very complicated idea. So I wanted to give you an opportunity to practice this again and again until you felt confident and comfortable with the content. What I'll do here is I will let you play around with these examples. When I go back and scan my notes, this page will be complete and it will have the broken down solutions. So I do want you to try this page on your own as well. Example 24. Give these problems a shot, see how they go, and see how your work compares to mine. When I write up the solution, I will break this down step by step so that you can see how I got from point A to point B, the solution, okay, or the simplified form. Very nice. Let's go back to the notes. We are now ready to simplify square roots. I actually really like this section. I have found that this can be kind of tricky, but stick with me and kind of think about the way in which I'm breaking these down. Also think back to how you write something that is in radical form in exponential form. Think about the relationship between those two things. And I'm going to try to break this down as simply as I can. And as always, if you do have any questions when you're at home trying this on your own, please don't hesitate to reach out. I'd be more than happy to walk you through some examples and even kind of, spitball with you on, what should you do here and, what ideas you have and how we can troubleshoot that if necessary. Okay, let's check it out. Okay, first things first, you know what a perfect square is, right? It's the square of an expression. What I've listed here are the numeric perfect squares, right? And of course, that's going to continue on to infinity. And then I've also provided to you the variable perfect squares. Notice the powers, 2, 4, 6, 8, 10, 12, 14. All of these are divisible by 2, right? All of those exponents are divisible by 2. Not the perfect squares, that's totally different. Your variable perfect squares, those powers are divisible by 2. That's something very important to know. So let me show you how we simplify. When we think about taking the square root of x to the 4th, we know that the root is 2. The beautiful thing about this is that if I rewrote this in exponential form, I would have x to the power over root, or x to the 4 over 2. Which means when I simplify this, I simply get x to the 2nd power. Now I want you to think about what happened here. I took the exponent of my variable base and I divided it by 2, my root. So, looking at my second example, my root in this case is 2. We know that my variable has a power of 4, so if we divide that by 2, we get x to the 2nd power. For my y, my power is 6, but my root is 2, so 6 divided by 2 is 3, and I'm done. So taking the square root of variables essentially means you cut the power in half. You divide it by 2. It works when you have even powers. When you have odd powers, we have to kind of tweak it a little bit, but we can still simplify, and I'll show you how. Let's look at each of these pieces. The square root of 49 gives us 7. The square root of x to the 8th, take the 8 divided by 2, x to the 4th. The square root of y to the 20th, take the 20 divided by 2, 10. The square root of z to the 18th, take the 18 divided by 2, 9. And we're done. Notice that I took the square root of each individual base. I just didn't write it out as the square root of each of these terms, or of each of these bases. I didn't rewrite it as such, but I could have. What I want you to do is move through these seamlessly. Square root of 49, square root of x to the 8th, square root of y to the 20th, square root of z to the 18th. Take care of these base by base. Notice I did not say the square root of 49x to the 8th. I wanted to take the square root of each base individually. Okay, make sure you're doing that. The square root of a perfect square always results in an expression that does not have a radical sign. When you actually use the square root and you've simplified an expression, that square root goes away. I don't want you to put the square root back. That doesn't make sense. It's like if you've ever played Uno, and of course I'm sure like almost everybody has played Uno, hopefully. I mean, if not, play some cards, it's fun. If you've played Uno, you have a wild card, right? So imagine that you have your cards and you place the wild and you tell the next person that it's yellow, and while they're about to play, you take the wild and you put it back in your hand. No. Somebody's going to call you a cheater. They're going to slap the cards out of your hand and they're going to say, don't play anymore, you're a cheater, right? If you use the square root on an expression and you actually apply the square root, it does not make sense to put the square root back. It's like taking a wild after playing it and putting it back in your hand. Don't do it. That's not fair. You can't do that. You actually used it. It's gone. So once you use it and you've been able to simplify to lowest terms and there is no radical anymore, don't put it back. I've seen far too many times students take the square root, for instance, square root of 16 is 4, but but then they write square root of 4, and they're like, oh, the square root of 4 is 2, and then they write square root of 2, and they're like, okay, it's square root of 2. And it's just like, how many wild cards do you have in your hand kind of deal, right? How many square roots do you have? I saw only one, and you used it. Once you use it, it's gone, okay? Perfect. Now, I want you to note the product rule for radicals. The square root of a times b is the same as the square root of a times the square root of b. Of course, for non-negative real numbers. This is why when we looked at this previous expression, I said to you, square root of 49, 7. Square root of x to the 8th, x to the 4th, etc., etc. I was able to take the square root of each base because that's essentially the product rule for radicals. Now, how do you simplify square roots if they're not perfect squares? Well, easy. Let me show you. Let's start by taking a look at the square root of 56. So right away, I'm going to notice that 56 can be broken down. When we think of breaking down 56, we want to say, is there a perfect square that's smaller than 56 that divides evenly into 56? Meaning 56 can be broken down into perfect square times what, right? So let's think about this. If I look at 56, I would say to myself, well, let's try dividing by 4, which is my second smallest perfect square. Oh, so that means 4 times 14 gives me 56. Is 14 factorable in terms of, do we get a perfect square times another value? No. 14 breaks down into 2 times 7. Those are not perfect squares, right? So what I'm going to do now is I'm going to say, okay, this means that the square root of 56 is the same as the square root of 4 times 14. 4 times 14 is 56. The square root of 4 times 14 is the square root of 56. I'm then going to highlight my perfect square. Since I've highlighted the square root of 4, I can say, well, I know what the square root of 4 is. It's 2. But I still have the square root of 14, so I'm going to leave it. I cannot break down the square root of 14, so that's it. You're done. This is how you simplify a square root. Let's do it again. Let's look at 175. Some of you are probably thinking, well, that's divisible by 5. That's true, but that's not a perfect square. Let's try 25, since that's a perfect square. So we take 175, we divide it by 25. Oh, and it breaks down into 25 times 7. Let's rewrite it. So we have the square root of 175 becomes the same as the square root of 25 times 7. I always like writing the perfect square first. For me, that's helpful because my eyes are drawn to that, and I remember that I need to evaluate it. So I'm going to highlight the 25 because that's a reminder to me that that is my perfect square. The square root of 25 is 5. And then I still have the square root of 7, so I can't just get rid of it. I simply rewrite, and we're done. Not bad, right? Let's do it again. 48. Okay, now one of the things I want you to be really careful of is the fact that when you do break down square roots, you want to find the largest perfect square factor. Okay, so if I'm looking at these numbers, 48 is obviously here, which means I'm going to be looking at these values and to see which one divides evenly. We know that 36 does not divide evenly into 48, neither does 25. But what about 16? Let's go ahead and do 48 divided by 16, and we get 3. Perfect. So we're going to write the square root of 16 times 3. Notice they're the same. Notice that 16 is my perfect square. So let's go ahead and highlight that. Then I can evaluate. The square root of 16 is 4, but I still have the square root of 3, so now I'm finished. At this point in the video, I definitely want you to pause. Try the next 3 examples on your own. Right now, I'm buying those of you who are with me right now watching this video, I'm buying you some time to try this. So look at the square root of 162, look at the square root of 90, look at the square root of 486, and try to find the largest perfect square factor. Write it as the perfect square times the rest, right, times the remaining factor. And then, of course, evaluate the square root of that perfect square, all right? Just like we've been doing. Hopefully this is actually going really, really well for you and that it makes a lot of sense. Let's take a look. The square root of 162. So I can look back at my list of values. I might start here. Notice 162 is obviously below 169. I know 144 can't go into it evenly. I know 121 can't. I know 100 can't. Let's try 81. So let's do 162 divided by 81. Yes, I found the largest perfect square factor. So I see that square root of 162 breaks down into square root of 81 times 2. See here that my 81 is a perfect square, so the square root of 81 is 9. So we get 9 square roots of 2. Let me give you some advice. If instead, when you saw 162, you said, well, let me divide by 2 and see what I get, that's another way of recognizing what the perfect square factor is. Sometimes with larger numbers, it could be helpful to go, a different route, like dividing by smaller numbers to see what that perfect square factor is, or by looking at the chart and trying to identify the largest and working your way down. So either way is fine. But you need to identify the largest perfect square factor. That's really the moral of the story. When I see square root of 90, immediately in my mind, I jump to 9 because 9 times 10 is 90. And we know that 10 does not have any perfect square factors. So we're going to write this as 9 times 10. This does not have any perfect square factors, so we know that the 9 is our perfect square. Let's go ahead and highlight that. Square root of 9 is 3, and we leave the square root of 10. Next, we have 486. When I look at 486, I say, I might actually work upwards, meaning like I'll divide by 2. Notice I get 243. That's not on my list. Let me take 486 divided by 4. I get a decimal. Let's do 486 divided by 6. That worked. So when I took 486 and I divided it by 6, I got an 81, which is actually really cool. So this means 486 breaks down into 81 times 6. 81 is my perfect square factor. Square root of 81 is 9, and we leave the square root of 6. 6 does not break down into any perfect square factors, so that's why we would be done there. All right, also notice 6 is not on my list of perfect squares. It would be here, but it's not. All right. Beautiful. This is how you would simplify the square root of a constant. Okay. Now, what we're going to learn is what to do when you have square roots of a variable and how they break down. We're going to start off really nice and easy, and I know I only have 6 minutes left, but you'd be surprised with how much we can actually accomplish. The square root of m to the second power. Well, our root is 2, our power is 2. 2 divided by 2 is 1. We're finished. The square root of y to the 12th. My root is 2, power is 12. 12 divided by 2 is 6. Finito, I'm done. Let's do it again. The square root of z to the 64th. Remember, this is the root is 2. 64 divided by 2 is 32. Done. Z to the 32nd power. We are taking the square root of 2 bases. Luckily, each of them has an even power, so cut them both in half. A to the 7th, b to the 10th. Now, this is where we get interesting. Take a look at part E, the square root of x to the 5th power. If that were a 4, you'd be able to divide it, right? You'd be able to cut it in half evenly. But it's a 5. But that just means I'm going to rewrite it just like I did with the square root of a constant. The square root of x to the 5th can be rewritten as the square root of x to the 4th times x to the 1st. X to the 4th times x to the 1st is x to the 5th. Product rule. Keep the base, add the powers. I'm going to highlight my perfect square factor. The square root of x to the 4th is just x to the 2nd power, but I still have a square root of x to the 1st, so I'm going to leave that. And that is how you break it down. Let's do it again. The square root of w to the 9th. Well, if it were an 8, I'd be able to do it, but it's a 9, so let's break this down. I can say w to the 9th is the same as w to the 8th times w to the 1st. Notice that w to the 8th is my perfect square factor. The square root of w to the 8th is w to the 4th. But I can't forget that I still have a square root of w, so that's going to stay. Perfect. With this particular expression here, personally, I really want you to look at these as separate pieces, because otherwise it's going to get really crazy really fast. So my advice to you all is to rewrite it. So we have the square root of 9, we have the square root of m to the 45th power, and we have a square root of n to the 22nd power. I'm going to highlight any perfect squares that I have. 9's a perfect square, n to the 22nd is a perfect square. Okay, the square root of 9 is 3. The square root of n to the 22nd is n to the 11, right? Because you cut that power in half. However, square root of m to the 45th, I can't cut that in half evenly. I could if that number were a 44. So I'm going to rewrite this as m to the 44th times m to the 1st. Are you seeing the pattern here? Every time I have an odd power, I just take one of them out. If I take one of them out, I'm left with an even power. The square root of m to the 44th is m to the 22nd, and we still have a square root of m to the 1st. Now you may be wondering, how do I clean this up? This looks insane. Any base that is not underneath a radical will be rewritten first, and the radical will go second. Okay, so we'll rewrite our answer as 3m to the 22nd, n to the 11th, right? Not under a radical, not under a radical, not under a radical, followed immediately by the base that is under a radical. And that is your final answer. We have time for one more. Let's take the square root of 18, square root of x to the 7th, and the square root of y to the 13th. I urge you to do the same thing. I do not have any perfect squares here, but that's okay. I know that square root of 18 can break down into 9 times 2, where 9 is my perfect square. I know that square root of x to the 7th can break down into x to the 6th times x to the 1st, where x to the 6th is my perfect square. And then lastly, I know that square root of y to the 13 can break down into y to the 12th times y to the 1st, where y to the 12th is my perfect square. We're going to evaluate each perfect square. So square root of 9 is 3. Then I have square root of 2. Square root of x to the 6th is x to the 3rd, and I have square root of x. Square root of y to the 12th is y to the 6th, and I have square root of y. Now let's clean this up. Every base that is not under a radical will go first. 3, x to the third, y to the sixth. And every base that's under a radical will go together under one radical. 2x, y. 2x, y. And that is your final answer. I know that was a lot of content, but I hope that's making sense. Try the last 3 problems on this page, but we will pick up where we left off later today. I anticipate being back on the live stream anywhere from 4 to 4:30 around there. So just make sure your notifications are on so that you can tag along if possible. All right. Excellent work today, everyone. I will see you later. Bye.